Hello everybody. Today we're going to do an interesting problem. So if you've ever dealt with complex numbers before, then you know what I is. I is the square root of -1. It's the imaginary unit. And so today we're going to ask a question and solve the answer. And the question we're going to ask is, what is the square root of the square root of -1? And we're going to solve the problem two ways. First, we're going to do it algebraically. And then we're going to do it geometrically or graphically to kind of show the power of that geometric understanding of complex numbers and why imagining complex numbers in the complex plane can be such a powerful mathematical tool and why that is so interesting. So we're going to do the answer twice. So let's do the algebraic method first. Alright, so we're trying to figure out what the square root of I is, and we have no idea where to start, but let's begin by just assuming that it's some kind of a complex number. It might be entirely real, it might be entirely imaginary, or it might be part real and part imaginary, we don't know. But the general complex number has a form of a plus bi, where a and b are real numbers, and I, of course, is the square root of -1. So let's assume that it has at least that form of some kind. Of course, a could be 0 or b could be 0, or they could both be numbers. We don't know yet. But we'll just assume that square root of I equals a plus bi for some kind of an a and a b. And we're going to begin, well, let's think. Where do we start? Well, one good thing to do, how about we get rid of that square root on the left? So we'll do that by squaring both sides. So if we square the left, we get square root of I squared. Well, that's just I. And on the right, that's just squaring a polynomial. So you're going to get a squared plus 2abi plus bi times bi, which is just b squared, I squared. All right, but b squared, I squared, well, I squared, that's the square root of -1, so I squared is just -1. So when you rearrange all of that, it's going to be I equals a squared minus b squared plus 2ab times I. So make sure you've got no questions on that, and we'll move on to the next slide. Okay, so at the top I've just copied over what we had at the bottom of the last slide. And I want you to notice something. I'm going to add 0 to the left-hand side of that equation. Now adding 0 doesn't change anything, so I is the same as 0 plus I. But I want you to notice on the left-hand side of the equation I now have a real part, 0, and an imaginary part, I. And on the right-hand side of the equation I have a real part, a squared minus b squared, that's a real number, and an imaginary part, 2abi. Well, real numbers can't be equal to imaginary numbers, and imaginary numbers can't be equal to real numbers. So I can break this equation into two different equations. I can set all of the real stuff equal to each other, and all of the imaginary stuff equal to each other, and I'm going to wind up with two separate equations. So I'm going to do that on the next slide. So there's where we started at the top. 0 plus I equals a squared minus b squared plus 2abi. And then on the next line down under implies, I've just broken the real pieces out and the imaginary pieces out. So on the left we have the real pieces, a squared minus b squared equals 0. Of course I flipped the order of that equation, but it's the same thing. And on the right I have I equals 2abi. That's all the imaginary parts. So I'm going to start with that. Let's start with I equals 2abi. And let's on the bottom line, I've got 3 steps. So the first step, I divide both sides of the equation by I. And I get I over I on the left side equals 2ab. Well, I over I divided by I, that's just 1. So 1 equals 2ab. And now if I divide both sides of that equation by 2a, I'll get a formula for b. b equals 1 over 2a, or 1 over 2a equals b, same thing. Now I'm going to use that on the next slide. So I'm going to use the two pieces we have now left on the next slide. And those two pieces are a squared minus b squared equals 0. Remember, I haven't done anything with that yet. And b equals 1 over 2a. And what I'm going to do is in that equation, a squared minus b squared equals 0, I'm going to substitute in what I already know b is, 1 over 2a. So working down the left column, a squared minus 1 over 2a squared equals 0. That's just substituting in for b. Now I'm going to square that term. I get a squared minus, well, 1 over 2a all squared, that's 1 over 4a squared equals 0. And now I'm going to add 1 over 4a squared to both sides. So on the left, a squared minus 1 over 4a squared plus 1 over 4a squared, that's just a squared. And on the right, 0 plus 1 over 4a squared is 1 over 4a squared, and that's the bottom left column there. A squared equals 1 over 4a squared. Now, I'm going to move to the right column. So I go from there to the right column just by multiplying both sides by a squared. And I get a to the 4th equals 1/4. Now I'm going to take the square root of both sides, and I'm going to get a squared, square root of a to the 4th equals square root of 1/4, or a squared equals the positive or negative square root of, a squared equals positive or negative 1/2. All right, so I have two possibilities for this. Because remember, anytime you take the square root, I'm going to have a positive possibility or a negative possibility. So we'll use the positive possibility. So a could either be equal to the square root of 1/2, or it could be equal to the negative square root of 1/2. And I'll do the positive square root of 1/2 first. So if a is equal to the positive square root of 1/2, well, the positive square root of 1/2, that's the square root of 1 divided by the square root of 2. And square root of 1 is just 1. So I get a equals 1 over the square root of 2. And 1 over the square root of 2, that's the same thing as square root of 2 over 2. That's called rationalizing the denominator. I just multiply the top and the bottom by square root of 2. Now if I take that a and substitute back in my formula for b, I find that b is also equal to the square root of 2 over 2. So if a is the positive square root of 1/2, then a and b are both square root of 2 over 2. All right, now I'm going to work on the second possibility. A equal to the negative square root of 1/2. And if I use that possibility, the math is exactly the same. A turns out to be negative square root of 2 over 2, and b turns out to be negative square root of 2 over 2. Everything works exactly the same as it did before. So, on the next slide, this is where we are so far. So I found an a and a b. In fact, I found two of them. So the square root of I is actually going to be equal to two things. If they're both positive, then the square root of I equals square root of 2 over 2 plus square root of 2 over 2i. And if they're both negative, then the square root of I equals negative square root of 2 over 2 minus square root of 2 over 2i. Now that shouldn't surprise you that the square root of I can be positive or negative, because the square root of any number is positive or negative, right? The square root of 4, if I asked you what's the square root of 4, you would probably say, well, it's 2, and that's true. But the square root of 4 is also negative 2. Negative 2 times negative 2, that's also 4. So 4 has a positive and a negative square root, and square root of I also has a positive and a negative square root. And we just found them, and that's our geometric answer. So we've solved it, I'm sorry, that's our algebraic answer. So we've solved it once, the algebraic method. So remember those answers, because they're going to come back later, of course, when we do it the second method. So now we're going to do the geometric method. So pretend that we haven't done any of the algebraic stuff. We're going to think about this geometrically. So remember that complex numbers, sometimes we plot them on the complex plane, where we have a real axis that's in red on my picture, and an imaginary axis that's in blue on my picture. And a complex number like 3 plus 2i, you would plot by moving 3 units to the right on the real axis, and then moving up 2 units on the imaginary axis, and putting a dot right there, and that would be 3 plus 2i. So that's one way we plot complex numbers. But there's a second way to plot complex numbers, and that's to use a radius and an angle. So for example, if I had a 3 plus 2i, I could figure out what the distance is to that point and what the angle is from the x-axis, and I could plot that point that way. Now there's advantages to both methods, the polar form, that's the radius and angle form, or the real and imaginary form. One of the beauties of the polar form is when we multiply complex numbers, then the radii multiply together, but the angles add. So, following that idea, let's go on to the next slide. So, again, we're going to assume that the square root of I is a complex number, but this time we're going to use its polar form. So square root of I equals radius times e to the theta I, where theta is the angle. So again, we have a radius r and an angle theta. Now, if we square both sides, we're going to get, well, on the left, we're just going to get, again, square root of I squared, that's I. And on the right, we're going to get r squared e. Now, remember when we square exponents, then it's like we multiply the exponent. So something, x to the 2 power cubed would be x to the 6, 2 times 3. So e to the theta squared is going to be e to the 2 theta. So that's how I got that formula on the bottom left, which is exactly the same thing as what I said earlier. The radii multiply, but the angles add. So, I, where is that on my complex plane? Well, that's my little green arrow right there, or my green dot, I should say, with the green line. Right? It has a radius of 1 and an angle of 90. And the square root of I, well, I don't know where that is yet, but I do know that its radius times itself has to equal the radius of I. And the radius of I is just 1. So what number times itself equals 1? That's the second equation on the bottom line right now. R squared equals 1. So what does that mean R has to be? Well, R has to be 1, of course. Right? So we found the radius of our unknown square root of I, and it has a radius of 1. Now, what about the angle? Well, I has an angle of 90 degrees, or pi over 2. And the angle of square root of I, we don't know it yet. But we do know that if we're going to multiply it times itself, the angles have to add to pi over 2. Because when we multiply complex numbers, the radii multiply, but the angles add. So that angle, whatever it is, theta plus itself, theta plus theta, has to equal 90, right, or pi over 2. So that means 2 theta is pi over 2, and theta is just pi over 4. So that is my first answer. Theta equals pi over 4. But remember, there's another way to get to I. I could go positive angles counterclockwise from the real axis up to I, or I could do negative angles clockwise from the real axis all the way around the other direction to the imaginary axis. And if I go counterclockwise, I have to go 270 degrees in the negative direction, which is the same as negative 3 pi over 4. I'm sorry, negative 3 pi over 2. So if I do that problem again, what's the square root of I? Well, if I'm working in the negative direction, negative angles, right, then 2 theta is equal to, instead of being equal to pi over 2, it's equal to negative 3 pi over 2, which means theta is equal to negative 3 pi over 4. So I have 2 answers just like before. I have square root of I equals radius 1 and pi over 4. or square root of I equals radius 1 and negative 3 pi over 4. So at the top, here's my two answers for theta. I equals negative 3 pi over 4 and I equals pi over 4. Radius in either case equals 1. Now that's enough, that would be the answer, but let's put it in the format that we're used to seeing, the a plus bi form. So how do I do that? Well, the complex number c is r e to the I theta, or it's r times the cosine of theta plus r times the sine of theta times I. So if we use r plus the sine of theta times I, well, first of all, our r's, those are just 1. So let's just plug in our, so that just becomes cosine of theta plus sine theta I. And now let's plug in our two values for theta. Well, the first one is cosine pi over 4 and sine pi over 4i. Well, the cosine of pi over 4, that's square root of 2 over 2. And the sine of pi over 4, that's square root of 2 over 2 as well. And we get I, square root of I equals square root of 2 over 2 plus square root of 2 over 2i, just like before. And if we use our negative 3 pi over 4, well, cosine of negative 3 pi over 4 is negative square root 2 over 2. And sine of negative 3 pi over 4 is square root negative 2 over 2i. Or, I'm sorry, square root negative 2 over 2. So we get the same answer as before. Square root of I equals negative square root over 2 over 2 minus square root of 2 over 2i. Now, real quick, I'm going to do one more thing, which is I'm going to pull up a little computer program that I wrote. All right, so here's a little computer program that I wrote. And the way it works is you put in two different complex numbers in the blue and the yellow, and it will plot them here on the screen in blue and yellow. So I've put in the complex number 1, 2 plus 1, 2i, 2 plus 2i, times negative 1 plus 2i, negative 1 plus 2i. And if you multiply those two complex numbers together, you get negative 6 plus 2i. Negative 1, 2, 3, 4, 5, 6 plus 1, 2i. Now, just as we said before, remember, when you multiply complex numbers together, the angles add. So the angle of this one, 2 plus 2i, that's 45 degrees. And the angle of negative 1 plus 2i is about 116.6 degrees. 116.6 plus 45 is 161.6. The angles of the two numbers that we multiply together add to the angle of the answer. In this case, the angle measured from here, 161 degrees. And the radii, the lengths, multiply. So, for example, the length of this one is 2.8284. 2.8284, that's 2 times the square root of 2. So 2 times the square root of 2 for this length. This one is going to be, let's see, 1 squared is 1, 2 squared is 4, 1 plus 4 is 5 square root. The square root of 5, right? And so the answer should wind up being, so we had 2 square root of 2 times square root of 5. So the answer should be 2 times the square root of 10. 2 times the square root of 10, so let's solve that. This would be 6 squared, it's 36, plus 2 squared is 4. That would be the square root of 40. Remember, the square root of 40, that's the same as the square root of 4 times the square root of 10. Square root of 4, that's 2, so 2 times the square root of 10. Sure enough, the radii multiply and the angles add. All right, so we found some answers before for square root of I. We said square root of I was the square root of 2 over 2 plus the square root of 2 over 2i. So let's use that answer. Square root of 2 over 2, that's about 0.7071. 0.7071. I'll do the same thing down here. 0.7071. 0.7071. And now when I click in the screen, boom. In this case, you can't see the blue angle because the yellow angle is right on top of it, but they're both the same. They're square root of 2 over 2 plus square root of 2 over 2i. And when you multiply them together, you get 0 plus 1i, which is just I. So sure enough, square root of 2 over 2 plus square root of 2 over 2i times square root of 2 over 2 plus square root of 2 over 2i equals just I. Notice again, the angles, 45 degrees, add to 90 degrees, and the radii, 1 times 1 equals 1. The angles add, the radii multiply. Now suppose we do the negatives. Negative square root over 2 over 2, negative square root 2 over 2 plus negative square root 2 over 2i times negative square root 2 over 2 plus negative square root 2 over 2i, and we'll click and it'll plot that for us. And again, same thing. There's our negative square root 2 over 2. Of course, the blue angle is underneath the yellow angle since they're exactly the same point. But look, the angles, negative 135 plus negative 135, that's negative 270. Negative 270, that's the same as 90, right? Negative 270, that would be going this way, 270 degrees to right there. That's the same as going this way to 90. And the radii, radius is 1, radius is 1, 1 times 1 is 1. So hopefully this shows you the power of the graphical method or the geometric interpretation of complex numbers. In fact, that makes this a problem we can almost do in our head, right? We know the angle is 90, so half the angle is 45, so we know the angle for the square root of I has to be 45. And we know the radius is 1, which means the radius of these two things has to be 1. So we could almost have solved the square root of I in our head using the graphical interpretation. All right, I hope you enjoyed that, and please, if you did, click like, click subscribe, and comment below if you had any questions on anything I went over. But hopefully you liked that a whole lot, and I'll see you next time.